That's Jianchao Ye from the Lawrence Livermore National Laboratory in Livermore, California. The presentation is titled Powder-Based Additive Manufacturing for Battery Applications. The floor is yours. Thank you.
Hi everyone. Can you see my screen? Great.
Yes.
Awesome. Yeah. So thanks for this opportunity for me to present some of our work. I'm working on different types of battery manufacturing technology. It's early stage, but I think it holds like a great promise for the future development. This is based on the laser additive manufacturing for the battery electrodes. So as you know, the current lithium-ion battery is based on slurry casting approach, which has big issues in the like high capital investment, especially because you have to recycle the NMP solvent, which is environmentally not friendly. So that involves like a large capital investment and also high energy consumption. So there's a trend to switch, from the wet processing to dry processing to reduce the cost and also potentially improve the battery by enable, thick electrodes or customized structured electrodes for the high rate performance application. So there are some dry calendaring approach has been developed in the industry, but they're still facing challenges like the choice of binders, the porosity control, like mechanical strengths, etc. So what we are doing right now is to develop a laser-based dry processing approach. How it works is, we're starting from very conventional lithium-ion battery electrode materials like NMC, PVDF, carbon black, those powders. We mix them into a uniform powder and then use like electrostatic spray coating to dry coating those powders into a layer onto the like aluminum foil, and then use a laser to apply the heat onto the powder layer, and that selectively melt the binder and bonded those materials onto the substrate. So you can envision that you can do some structuring there and some customized shape to give you what you need on the battery electrodes, and you can also do like layer by layer coating, and also those untreated areas you can recycle the powders for reuse to reduce the material waste. So it has advantage like lower the energy consumption. It has a faster like a cooling heating rate that can enable some like unique tuning of the mechanical or material properties. The bonding strength is pretty good, and and you can do like multi-layer coating and high like production rate, etc. So this is how it looks like from the powder feedstock. Conventional chemistry using some of developed two-step mixing approach. This is show some SEM images show how uniform it is. And you from this zoom in image, you can see those PVDF and carbon black coated on the NMC polycrystal particles there. So starting from those mixed powders, we apply this electrostatic spray coating where there is a high voltage electrodes at the end of the nozzle. When the powders bring out from the nozzle, those particles are charged with those electric field and then deposited onto the grounded substrate. And here is how it works. And this is a layer of the aluminum foil laid down on the floor. And we can do spray coating on there, multiple passes, and then you can get a relatively uniform coating after that. And those like powders that are surrounding there can be recycled and reused in the spray, and that also shows consistent powder coating uniformity. And this is how it looks like after the spray coating. Quite loose powders, but we can do the post calendaring to densify it. So with those layer of the